Assalamualaikum and good morning to the panel. My name is Muhamad Afiq bin Yusri and my student ID number is 2019 290 and 914. My supervisor name is Sir Muhammad Hanif bin Mat at Muhammad. So I'm here to present my FYP topics, which is the the design of wind tunnel specimen stand to analyze the rotation of the shuttlecock. So for the introduction part, the game of shuttlecock and battledore is thought to have given rise to badminton as we know it today in the 1860s, most likely at Badminton House in Avon. The Badminton Association England was founded in 1863, and the same year the game's formal rules were established. These regulations were shaped by the characteristic of the feathers shuttlecock. Basically, when you started playing badminton, it is recommended to use a synthetic shuttlecock which consists of plastic or nylon material. The cost of using synthetic shuttlecock is lower since they are more durable. Compared to the synthetic, the feather shuttlecock offers higher aerodynamic lift, speed, and trajectory. Because of the design of the feather shuttlecock, a player will be able to hit it properly. In order to study the performance of a feather shuttlecock, designing a wind tunnel plays an important role. For the problem statement, the behavior of the shuttlecock relies on its speed of motion. A wind tunnel is necessary to understand the forces acting on the shuttlecock. Holding the shuttlecock in the right place when the wind is blowing was the key issue. There are two objectives in this study. The first one is to design a mounting rig to analyze shuttlecock performance under different speed using a wind tunnel. And the second one, to determine the relationship between rotational speed against airflow speed of the shuttlecock. Scope and limitation of this study. The first one, this study is to design a wind tunnel mounting rig in order to analyze the rotation of the shuttlecock. The second one, the mounting rig will hold the shuttlecock in fixed position to avoid error in taking data. Analysis of the study will be done using software that has already been installed on the provided computer in the Aerospace Laboratory FKM. The next one is our limitation is we only use one brand of shuttlecock, that is RCL Black. The shuttlecock performance also will be focused on the speed, not on the force directed to the nose of the shuttlecock. Maximum airspeed used in the wind tunnel is limited only to 45 meters per second. But it is impossible to use until the maximum airspeed because this is due to the safety and the noise emission. The height of the mounting rig also will be 25 cm at the center of the test section of the wind tunnel. And the length of the hanging rig will be 13 cm. Next one is the literature review. Okay, the first is shuttlecock. It has been weighed between 4.75 to 5.50 gram, and it contains 16 feathers, each measuring 62 to 70 millimeter. The cock measure 25 to 28 millimeter in the diameter. The feather form a circle that is between 58 and 68 in diameter. Wind tunnel. First, we need to understand what is wind tunnel. Wind tunnel is a tunnel that is full of air or another gas. It is frequently used to investigate the flow past models of airplanes, buildings, and vehicles, among other things. The maximum speed for wind tunnel in this study is 45 meters per second. The test segment has a length of 12.5 cm. Cross-sectional area is 50 cm times 50 cm. Overall dimension of the wind tunnel is 8.8 meter times 2 meter times 2.3 meter. For the rig, we place the rig in the center of the wind tunnel, that is 25 cm above the ground. And then we need to make a thread at the end of the rig to hold the rig in position. This is because the wind tunnel is used to test the F1 school car in aerospace laboratory. And usually the material that used in this rig is stainless steel, and the rig is combination of the bearing to rotate the shuttlecock freely. For the calculating forces that hit the shuttlecock, first we need to draw the free body diagram of the shuttlecock, and then we notice that along the x-axis there are only two forces, which is wind force and the drag force. So we can summarize as F in force in the x direction equal to 0, and then we get force wind equal to Fr, which is drag force. Force wind equal to Fr. Fr, we already know the formula, which is 1/2 rho v square times area. But forces of the wind, we have to consider the potential energy, kinetic energy, and then we get the whole formula is force equal to 1/2 rho v square times area. To observe the rotational part of the shuttlecock, we have two tools. The first one is non-contact tachometer, and the second one is digital encoder. For the non-contact tachometer, it do not make any physical contact with a rotating shaft to obtain the measurement. This meter often employ a reflector on the shaft to be measured, and an infrared laser pointing at the rotating shaft. Each time a shaft rotates and the laser meet the reflector, light bounce back to a sensor in the tachometer. The tachometer counts each time this occurs. So it measures in RPM unit. It range 2 until 99,999 RPM. Its accuracy is plus minus 0.05% plus 1 digit. For the digital encoder, they provide a fixed number of pulse per revolution, which is PPR. By counting this pulse, one can easily find the number of the rotation or its fraction completed by the motor. 3 quadrature decoder and 2 counter or timer unit. All data can be streamed synchronized to the host memory. An oscillator with 36 MHz measure high-speed signal very accurately, and it has 16 bits resolution. For the methodology, the speed of the wind tunnel we divide into 5 sets of data. which are 7 meter per second, 14 meter per second, 21 meter per second, 28 meter per second, and 35 meter per second. The rotational speed of the shuttlecock will be measured using a tachometer to detect the number of spin of the shuttlecock in the wind tunnel during those 5 airspeed are under 50 seconds. Thus, the relation between rotational speed and airflow can be recorded by a table and a graph. A further methodology part, we using flow chart. Okay, we have define problem, background research, specify requirement, brainstorm, develop, and test solution. What I do in FYP1 is define the problem, do background research, and specify requirement. Besides that, I will do it in FYP2. Define the problem. To get a point in badminton, the shuttlecock need to hit the ground in the opponent half of the court. It includes the line. A good shuttlecock should have a good flight trajectory and less rotation to produce high speed. For the shuttlecock to hit the ground, a player need to hit hard the shuttlecock beside the properties of the shuttlecock. Background research. The next stage of the study, gathering information about the shuttlecock and its testing takes place. The diameter of the skirt is 64.99mm. The length of the feather is 60mm. The length of the cock is 25.172mm. And the mass of the shuttlecock is 5.054 gram. The wind tunnel is the place where the rotational speed of the shuttlecock can be tested. It is a wind tunnel with an operating circuit. Approximately 45 meter per second is the wind tunnel top speed. The test segment has a length of 12.5 cm and cross-sectional area is 50 cm times 50 cm. Specify requirement. Calculation of the force as we discussed before. And then the bearing outer diameter to hold the shuttlecock must lower than the diameter of the nose of the shuttlecock, and the inner diameter of bearing should fit into the rod size based on the NTN bearing catalog. A 6x5, 6x15 times 5 dimension is the most suitable bearing, as the rod is 6mm and the diameter of the shuttlecock is 25mm. It should fit the nose of the shuttlecock. The bearing should have low friction, can be optimized for low vibration, which enable high rotational speed. They also should support radial and axial force to rotate freely. The material type of the rig also should be impact resistant and high strength to sustain its position. Two different diameters of rod were used in the study, which are 9.5mm and 6mm. The 9.5 mm will be the stand and the 6 mm will be the hang. The height of the rod is 225 cm and the hanging rod is 13 cm. The result which I need to relate with the objective. The mounting rig could perform without any bending when the airspeed is switched on. The rig also should have improvement from the existing design, such as preventing any excessive vibration on the rig. The rotational speed should be increased when airflow speed is increased. The bearing should rotate freely as the airflow speed hit the shuttlecock. The FEA analysis was done using CATIA software when the maximum airspeed, which is 35 meter per second, produce the maximum force. And then you can see the picture, the full design of mounting rig in the drawing CATIA, and then the deformation of the rig and also the von Mises stress.